Hello. Hello, can you hear me?
Yes,
Yes,
sir.
So, yeah, so before I start, do you have any particular questions that what was done in the last class? I guess that you guys, all of you have submitted your assignments. So, there's also the assignment questions, but the assignment questions will be discussed by the TAs in the tutorial session tomorrow, in any case. Also, regarding this, what we have done till now in graph algorithm and whatever we'll be doing today, so that will be kind of given as there will be a problem set uploaded by the end of the day or end of tomorrow, along with an assignment that will be due maybe next Monday, something like that.
Sir,
Yeah.
Sir, I wanted to say that could you please give another assignment, might be which don't have any weightage in the exam, but the difficulty level is a bit less than the given than the assignments given, because sir, this course is quite new to many of us, and we really wanted to have some practice before solving on these questions. Which
Right. So that is the reason why I am posting the problem sets. Have you seen the problem set?
Sorry, sir, I haven't seen them.
Yes, the problem sets are exactly for that reason.
Okay, sir.
So in the web page, there is a problem set that are uploaded. Okay, they
Okay.
have lot more questions. Okay, there
Okay,
many
sir.
of them are very easy to do. Many of them are hard. It's a mixture of them, and that's exactly the reason I am uploading problem sets.
Okay, sir. Thank you, sir. Thank you.
So please look at the problem sets. Okay, you have access to the web page, right?
Yes, sir. Yes.
Yes. So in the web page, you will have in the bottom there is a problem set. I think right now there's at least one problem set has been posted, maybe two, I don't remember.
Okay, sir.
Okay, and one more problem set will be posted very soon. So see, I mean, as you know, unless you solve problems, you will not be able to do anything. Okay. So there are lots and lots of problems that are available anyways in the market. You can pick up any book on algorithms, and these topics are all of them are standard topics in all books. Okay, so you can pick up any book and do the exercise from there. And on top of that, I'm giving you problem sets, which is another collection of maybe 10, 12 problems in each problem set, which you guys are expected to solve. Okay.
Yes, sir.
So, okay. The other thing is that while you are doing the assignments, okay, like this assignment was on sorting and binary search and all of that. But I'm hoping that you guys are not completely missing out on the graph algorithms part. Because if that is happening, then you will be really struggling once again. Okay. In fact, to be, I mean, for you guys, for your batch is kind of a lucky batch because you are getting big breaks in the middle. There was this puja break in the middle, and now there's the Diwali. There will be one class missing in the next Thursday. So because of that, you will have time. Of course, you can have fun on those times. Okay, which is, I mean, I'm of course what you are expected to do also. But at the same time, you should also try to catch up. If you are struggling with any course, use this break to catch up on whatever you have struggling to. Okay. If you are struggling on any topic, I mean, this is something I don't know how more can I emphasize this thing. But if you are struggling on any topic, please write to us that this is the topic, that can you please revisit this topic, or can you please explain us this problem again. Either I will do it in class or the TS will do it in their class. If required, I can take extra classes also for this kind of problem solving or the doubt clearance kind of stuff. But these things you guys have to take the lead. If you are not interested in asking, if you wait till the end mid-sem or something like that before you start reading up stuff, then believe me, you are in a big problem.
Sir.
Okay. Yeah.
Sir, I have a suggestion, sir.
Yeah.
Sir, like we have our tutorial class, which is on scheduled on Friday, let's say from 7 to 8,
Right.
wherein we actually do some like some discussion, theory discussion, also some problem discussion also.
Right.
Sir, we might can we do this? Like, this is a suggestion. I don't know how feasible it is, but sir, let's say the problem sets that you're giving.
Yeah.
Maybe let's say I take let's say a chunk of it.
Yeah.
Like, let's say the tutorial class already starts in the evening, like 7. Right. So maybe let's say 1.5 hours before the tutorial class,
yes,
a problem set is given, and it is not like it is supposed to be like a review exam or which is not graded, but we will have like that 1.5 hours wherein we will solve those problems, and then in the tutorial session we can have a discussion on that. So that would give us, like, apart from like whatever concepts we are learning, are we able to apply them to solve particular, for example, let's say I learned DFS, and now am I able to use that concept to, let's say, for doing a topological sort type problem or something like that, in like 1.5 hours type, and then it will be followed with discussion, so that whatever and the level might not be very difficult, or it's just an average difficulty, so that it can be like a simulated test followed by a discussion type thing. And I don't know, it might help us actually understand, okay, we have learned something, and also we are able to apply them in a constraint in a given certain amount of time. So can that be
okay? So I mean, so this is exactly the reason why the problem sets have been given. Okay, problem sets are not graded. Okay.
Yes, sir.
I mean, what is expected of you guys is to do the problem set. It's not a time bound. I understand. That's where the difference between maybe your proposal and my thing is. That I'm not giving you a time when to do it. Okay. But here is the problem set, maybe 10 problems or something like that. Okay. You try to solve it. Okay. If required, even you can discuss with your friends for that matter. Okay, because this is also kind of a part of it that is important. Okay. But then come to the tutorial session
and then have a discussion.
And then have a discussion on that.
Correct, sir.
Okay, problem sets are there for discussions. Okay. If you guys don't come with doubts, or if you come to the tutorial session without any question, okay, then the TS will possibly do some topics.
Yes, sir.
But if you have doubts, that's the first thing. That's the tutorial session is exactly meant for that. Okay. And yes, the problem sets have been given just for that particular purpose. So maybe for tomorrow, say for example, I'll be happy to. So Omkar is here. I think Omkar has already made up a problem set. Maybe if you guys want, we can give a slightly shorter problem set, or maybe we will just. So Omkar, this problem set that we are yet to upload, it is on DFS and BFS, right?
No, sir, it's on sorting only.
Okay, so it's on sorting. Okay, so can you maybe then try to make up another some problems on DFS and BFS?
Sure. I'll get
and we will try to upload both of them maybe by tonight.
Yeah, sure.
And then we can. Yeah, in case I also don't do it, you can, after doing it, you can even post it on the classroom.
Yeah, sure.
And then in the next tomorrow's tutorial, you guys can can discuss that. And again, I expect you guys to come back after trying out these problem sets at least. I'm not saying that you solve the problem sets perfectly. That I understand that can be, some of you might get stuck. But at least it should not be that you're seeing the problem for the first time in the tutorial session. Then it is no fun, no use also, some level. Okay.
Okay, sir. Yes, sir. Thank you, sir.
Sir.
Yeah.
Sir, can I just suggest one more thing?
Sure.
Sir, so whatever is being uploaded on the web page, most of us actually don't get any notification, or we don't get
web page thing is not notified. Okay.
Right. So maybe, so would it be possible for you to also upload it on the Google Classroom?
I mean, the problem sets and all, you're saying, okay, maybe I will just try to post one something in the Google. I will try to, from now on, whenever I do something, I will try to at least post some message in the Google Classroom saying that something has been uploaded in the webpage.
Okay.
Okay.
All right. Thank you so much.
So that can be done. Yeah, but you are expected to kind of go and look at the webpage regularly, because I tend to put up these even recordings and all pretty frequently. I have not done it for the last class, but that's a different story.
Okay. So you're not uploading any lecture videos other than the class one, right?
Except for the last one, every other lecture video has been uploaded.
So no, I meant you're not uploading any.
No, I'm not
other
uploading
lessons,
any lecture videos other than what has been done in
the class recordings. Okay.
Yeah.
Thank you.
I mean, we are still almost, because since this is your first class or first course in algorithmic thinking, okay, you have done possibly some programming earlier, but you have not done this algorithmic thinking that much. Okay. So it will take you some time to get used to it. That's why what we are doing now is quite very basic stuff. Okay, and this is how it will be in some sense till the mid-sem for certain matter. Okay, so yeah, so it is not very hard to pick them up, believe me. You will find it tough, but as soon as you solve a few problems by yourself, you will be in good shape. Okay, so I mean, just do some problems. I mean, do the problem set, take up any book and try to solve them from those chapters. Anything, okay? You will be be very much in the you will get used to it very easily. But if you don't put in that effort, then it's not going to work. Okay.
Yes, sir.
Yeah, and I am of course uploading web things, videos, and all. But believe me, these are all standard topics. Okay, whatever has been done till now, and from whatever will be done for most of the class is very standard topic. There will be very nice lecture notes and videos on the internet also. I mean, if you think that you are not understanding some particular concept as what I have explained, please just search it in the Google and listen to that. Okay. Even then, if you have doubts, of course, I mean, I am always there, or TAs are always there. You can come anytime. Okay? But I'm saying is that you have to put a little bit of effort from your side, and that's it. I mean, if you attend this class properly, ask questions, and just solve the problem sets, solve the assignments, you are already in good shape. I mean, that's how I plan this. I mean, I design my courses usually. But if you, at least you have to do that much amount of effort. Solve this, to listen to this class videos, class lectures, and all. And again, this is something I don't believe that I have to tell it to you guys. You guys are third year BStat students, so you guys should be knowing this one. That if any one of you feel that, oh, I am kind of not understanding this course right now, but if I just put in some little bit effort, I will be done. So I will just wait till I catch up with the class. Okay. Don't do that. If you are struggling, stop me. Just let me know. There's no shame in that. Okay. It is much easier to stop me from going ahead and asking me doubts and asking me to repeat again and again than you not understanding in the class and trying to make it up in the last, just before the midterm or just before the end. Okay. So please ask me doubts. I encourage you like anything.
Sir?
Yeah.
With regards to this issue of asking doubts and not being ashamed or anything, I just wanted to point out that in some cases, the concern is not about being ashamed, but about the fact that a lot of time is being spent on a handful of topics which are leaving the others
No, don't
largely
worry about that. Don't worry about that at all. Okay, you leave this responsibility of covering topics and all to me. Your job as an individual, all of your job as an individual, to learn what is being taught. Okay, to understand what is being taught. If you don't understand it, that's my fault. You can ask me again and again. Okay.
No, sir, but I was just saying that if we go on like this, then at the end of this, will some topics not be rushed over?
No, it will not be. I can promise you. If required, I will teach less.
So that is also...
No, don't worry about that. That is much more. Believe me, I have taught this course many times in many institutes. Okay. I would still prefer you guys to ask me questions as much as you can.
Okay, sir.
Okay. Because see, again, as I tell you, all the questions will happen in the beginning. Okay. Because as soon as you understand this whole this concepts of this stuffs, okay, this initial algorithmic way of thinking and all, you will find everything else easy. But if you don't understand this part, if you lose out on this part, things will become hard. So that's what I'm again and again saying. Please ask. Don't worry about this, what course has to be done, how much has to be covered and all. Believe me, everything will be taken care of. There will be no rushing at any point of time in the whole course, and we will be covering more than what is given in the syllabus. Okay.
Sir?
Yeah.
I just wanted to say this, since we are not in hostel right now, so we cannot have some extra discussion with any of the TA right now. So can we get some contact detail to
you have the contact details? The email address and all are all in the web page.
Email.
I mean, emails are the most perfect way of reply. Okay.
Okay.
If you want to talk to any TAs, just mail them. Okay. I think my phone number is an open secret. I think everybody of you already have my phone number. I mean, do feel free to call us. I mean, don't call us at random time of the day, but I mean, you are fully allowed to call me if you have any doubts. Okay. And just send a mail to us, any of us, the TAs, me, send a message to the classroom. Okay. See this. I don't think the biggest problem that is happening because of the lack of physical classes is that you guys are not being able to discuss among yourselves. And that's a big disadvantage. Okay, discussing among yourselves, you will have understood it much easier, much simpler. But that, again, I mean, of course, I mean, what can be done about this? I mean, hopefully things will improve. Maybe after Diwali, I think might allow some of you to come back to campus or something. Currently, the West Bengal government has allowed colleges to start from 15th of November. So maybe you guys, all of you have got this information already. So has the Dean's Office told you anything about anything of this kind?
Not officially.
Not officially. So I'm hoping that you will be allowed to come back to campus. At least since you guys are third year students, so most likely you will be allowed to come back to class, to physical classroom, the 15th of November. But we'll see what happens. Yeah, but regarding contact, yeah, I mean, if you want their phone numbers, just send a mail to them. Can you please provide us your phone number or something? Okay. Yeah.
Okay, sir. Thank you, sir.
Yeah. Any other questions? Any other doubts, suggestions? I'm open to everything. If not, so any doubts about the DFS thing that was done, depth first search that was done in the last class? Yeah. Okay. So if nothing, then let's move on to the next thing. Okay. So let me share my screen. Can you see my screen?
Yes, sir.
So
Yes, sir.
so what did we do till now? So we were basically doing graph traversal, right? And basically idea is to basically all that we have to do is that visit all vertices. That's all that we are supposed to do. Okay. Now, because we want to visit all the vertices, we also don't want to revisit a vertex multiple times or too many times, right? So we need to do some kind of a bookkeeping to ensure that where we have gone and where we have not gone, right? And this one, in the last class, we discussed this thing called depth first search. Now, in the depth first search was one of this kind of bookkeeping techniques. And the idea is that you keep on going as far as you can. And when you have no other place to go, basically, it doesn't have any other, you land up a place where it doesn't have any neighbor, which is new. Then you retrace back one vertex and then go and check whether so maybe I can just try to, so this one, right? So this one was the DFS thing. You keep on going as far as you can, and when you get stuck, you kind of go back to the place, the previous vertex, which in this case was C, and then see whether you can go anywhere else. And now, okay, you cannot go anywhere else. Let's go back one more step. So now we are at E, and they say, okay, can we go somewhere else? Yes, we can. Now we continue again. Again, I get stuck at D, and then we find out that okay, we cannot go any new place from D, and so we then come back and say that okay, let's come back to the previous one, which is F, and then we go to something else that we have not seen. And like that, we basically cover the whole graph. And the biggest important thing here is that these two things. Hello?
Yes,
Yes,
sir.
sir.
Yeah, suddenly I thought that the connection went off.
No, sir.
Okay, so the two important things is that first of all, is that the runtime was basically that we were going along every edge exactly twice. Once from say there's the edge UV, I'm going from U to V and V to U kind of stuff. And if you guys remember this one, how we were doing it is basically by kind of deleting. Once we go from U to V, I remove V from the neighbor of U. So the neighborhood of U itself kind of gets shrinking regularly, right? So basically, this becomes order of E plus V, right? And the second thing that was done was that to do this whole stuff, what we used is a stack, right? Hello.
Yes, sir.
Yes, sir.
Yes, sir. Yes, sir.
Sorry, I mean with a dead silence from the other side, I'm getting very confused about. Yeah. So you have a stack, right? Good.
Right.
So this was a DFS thing. Okay. Now, of course, DFS has some usage. I don't know whether you guys have gone over it or not, but this is something that I left you guys to think about it and discuss. I am not going to do it here again. I am still asking you to go back and think how can you use DFS to get topological sort. Okay. Please think about DFS. Think about how you want to do it with topological sort, and come back and discuss it with your TL tomorrow. Okay. In fact, this is available everywhere, but it will at least help you to think about how does a DFS tree looks like. Now, today we will be doing the next other kind of stuff. So this is a called a breadth first search, and this is basically idea is that if you are at a particular vertex, okay, you look at or you visit all of its neighbors. So basically, you have a vertex. Say you, I look at who are your neighbors? Okay, you have 4 neighbors. Very good. And now I'll go the first neighbor. And then, okay, you are the first neighbor. So once I'm done with this one, I'm done. And okay, you are the first neighbor. Okay, now how many neighbors do you have? I will go and visit all of them. So maybe then I'm done with this all the first neighbors. Then I say, okay, what about the second neighbor? The second neighbor will say, okay, see, I have only 3 neighbors. I have a neighbor to this one, and a new neighbor. Okay, but since I have already done these things, they have already done, so I am only going to keep track of this new neighbor, and so on. So I will first do this vertex, then I will go over all of its neighbors, then I will go to the next line and do all of its neighbors, and so on. Okay, so there is an ordering of all the neighbors of all the descendants of V, and I will cover them accordingly. So let me see how. Let me give you an example of this. Okay. Yeah. So here again.
Sir,
so
why have you classified it as an algorithm for producing a spanning tree? I mean, those are equivalent, but
so these are also equivalent. So you can produce a spanning tree because you are actually anyways going to the edges along which you are going to find a vertex for the first time. Okay, so
right.
Those edges will form a tree. Okay,
right.
Why?
Because we are not revisiting any vertex, so there is no cycle formed.
They cannot be a cycle form. How can they be cycle form? Because that is the place from where, I mean, if there is a cycle form, then you can say that
we
okay,
are visiting, right.
I mean, this is the first time when we are visiting a vertex, right? Those edges will.
Right.
And they will give you, so therefore, what will be output is that those set of edges is a spanning tree. Okay.
Yes, sir.
So if I ask you that, okay, here is a graph, can you give me a spanning tree? You can do either DFS or BFS, and you will give a spanning tree. Okay. By the way, there can be other spanning trees also that are not produced by DFS or BFS, but that's fine. This is 2 ways of producing spanning trees, but there are many other spanning trees. Okay, is it clear or should I explain?
Yes, sir. Yes, sir.
Fine, right?
Yes, sir.
Okay. So say here, let me again, like I did in the last class, I will first do this algorithm, okay, and then I will show you how to do the big scooping. So for now, don't look at what is here in the top, okay? Just look at the graph. Okay, so I start with say H here, okay? This is the H. Then I will look at all its neighbors. So who are its neighbors? See, G. Okay. At this point, I go to G. Okay, very good. Then I look at what is right, sorry. So G is neighbor. Okay. Now I look at all the neighbors of G. Okay, so E, F. Okay. Now see, at this point, E is the first neighbor of first child of G. So I tell E, okay, who are your neighbors? So, okay, my neighbors are C, B, and D. So who are the neighbors of? Now I am done with this E. Okay. Now who are the neighbors of F? So you kind of do it generation by generation. Okay. Basically, that's how this tree happens. So it's something like you first go to your grandfather and say, okay, who are your kids? Okay, you have these three sons. Okay, fine. Now let's go to the first son. Okay, who are your kids? Some set of kids. Now instead of going to their kids directly, I said, okay, the first son is done. So now let's go to the second son of my grandfather. Who are your kids? And you write them. Okay, and so on and so forth. So at this point, so E is at a level 2. Look at it. E is at a level 2. Why? What is 2 means? So if H is a level 0, G is at level 1. So G is just 1, is basically the child of H. So it is level 1. E and F are of level 2, right? At this point, I am going on level 2. Now E is saying that, okay, who are your neighbors? C, D, and B. That means C, D, and B are at level 3. But at this point, I am not done with level 2, right? I am just done with E. So I have to go back to F. F is on the level 2. And I ask, who are your neighbors? Okay, F has a neighbor E, but E is already visited, so no problem. F has a neighbor D, so D is visited. Okay, good. So that means there's nothing more to see. So that means I am done with level 2. Now we go to level 3. In the level 3, what the first thing that I saw was C, right? So, okay, who are your neighbors of C? No. So C has a neighbor B, which is already visited. Okay, C has a neighbor G, which is visited, so nothing else to be done from here. Good. Then you go to the next one. So let's say we are at level 3 only at this point. Okay. So who are its neighbors? Is B. Okay. So B is this neighbor, right? And then we said, okay, who are these neighbors of B? So A. Is there any other neighbor? No, B doesn't have any neighbor. I'm still not done with level 3, by the way. C, B, and D was at level 3. C is done, B is done. I'll go to D. So D has a neighbor B, which is already visited. D has an A, which is already visited, right? And then I said, okay, so level 3 is done, right? So I have to go to level 4, and the level 4 is A. And I said, okay, A doesn't have any neighbor, and that's it. Okay. So I visit them level by level or generation by generation.
Right.
Clear to everybody? How? Yeah, go ahead.
Could you explain this once more?
Yes, I will explain that. So what is it? Would you have any? Somebody was saying.
So I was saying, will there be any difference in the algorithm for undirected graphs?
No, the same. They will be same. Okay.
Okay.
I mean, identically same. I mean, here we are just only going to send neighbors. We mean out neighbor, and there is just neighbor.
Okay.
So okay, so let's do it again. Okay. So I start from H. Okay, this is I start from H. So think of H to be your great grandfather. Okay. Now H has, question is that H is the generation 0. Say, right? You are drawing the family tree from H. The family tree is not a very good way to think about it. Okay, because there's a lot of complications here. But yeah. But still, okay, let's think in some direction. Okay, maybe
We might think it as
Fluid flowing down.
pipes.
sorry.
Sir, you can think of it as fluid flowing down.
Yes, sir.
Fluid flowing down. Okay, so let's start with fluid flowing down. Okay, so H is the starting point. Okay, now H is at level 0, right? The topmost level. Okay, I mean the fluid might flow up also later on, that we'll see, but that's fine. Okay, but this is the starting point. Then who are its neighbors? Neighbors, I mean out neighbors. Okay, so G is its out neighbor, right? It has only one out neighbor, and that is G. So this G is at level 1. So okay, now is there any other thing is level 0? Okay, level 0 only had one vertex, of course. Done. So I'm done with level 0. Now I'm casting go to level 1. Okay. Level 1, okay, what are the vertex? Okay, G is the vertex. Good. So G, what all neighbors do you have? I will list out all the neighbors. So like E and F. Okay, so at this point, E and F are at level 2. Okay. Okay, E and F are at level 2. But okay, good. But level 1, are you done? So level 1, there is only G. That's it. Nothing else is there. Okay. In that case, I go to the level 2 now. So level 2, I have two vertices, E and F. I start with E. Who are your neighbors? Okay, the A neighbors are B, C, and D. Right? So I write down the B, C, and D neighbors. And so these are all neighbors level 3. Okay, B, C, and D are at level 3. Fine. Now, okay. So now, but level 2, I'm not yet done. So level 2, there's one more vertex, which is F. Okay. Now F, what are your neighbors? Okay, F has a neighbor E. Okay, that is already visited. Nothing to do that. Okay, F has a neighbor D, which is also already visited. So F doesn't give you anything new. Okay, so that's it. There's no other vertex on level 2, so I'm done with level 2.
Sir, could you please repeat the third step? Sir, after E, what are we doing?
So after E, okay. So after E, so let's see what is the level. Can you somebody say what do we mean by the level here?
The minimum number of steps required to reach the vertex.
Right. Level is
From the
basically
root.
happening the minimum number of distance or minimum number of edges required to go from H to that vertex. Okay. So G is at level 1 because I can go from H to G in one step. E and F are in level 2 because I can go from H to E and F in 2 steps. Okay. Fine. So at this point, at E, I am at level 2. Okay. In level 2, I will first look at the first vertex in level 2, which is E here in this case. And say, okay, what all other vertices, all the neighbors that are there? I've recorded all the vertices that are there, neighbors, which is B, C, and D. Right? Good. So these are all level 3, by the way. Think of it. The B is at level 3. H, G, E, B. Okay. But question then, why is B in level 3? Why not in level 2? Can B be in level 2?
So it's not adjacent to any of the level 1 vertices or the so it can't be level 2.
Yeah, because it is not. Because if it is in level 2, that means there is some other path from B to H or H to B in 2 steps, right?
Okay, right.
In that case, I would have found it before.
Right. So once we've selected a root node, what we've done is already selected a hierarchy of the nodes. We've already separated them into levels.
Right.
Now
We've
the actual
already
progression.
submitted a hierarchy.
Right. And now the progression of the algorithm will only determine which node gets which children nodes. That could change depending on the order of the children that we write down. So in this case, if we were to go to F from G before we went to E, then we would find that
then we have got
D would have been a child of F and not E. So that ordering could possibly change, but then still the level 2 will still comprise of A, B, C, and A, B, and C. Right.
Yes, there will be all the labels of every vertex is determined as soon as the root node is determined.
Right.
The level of any node is the minimum distance from the root node to that. Yeah.
And sir, what you're writing on the top is what's the data structure on top?
Okay, I'll come to that. That's called cube. I'll come to that.
So sorry, sir. Could you please repeat?
So data structure that is written on top. I will come to that. Okay. So what is being used here? It's a cube. It's
okay,
cube.
Sir.
Cube.
Okay, sir.
Okay.
Sir.
Yeah.
Sir, sir, the algorithm at any particular level chooses which one to visit depending upon its representation, right? Like, I mean, how,
depending on how the
let's
ordering
say,
of the
yes, for example, for G, whether it goes to E first or F first will depend upon how the adjacency list is stored, right?
Right, exactly.
So, sir, I think someone asked this question that regarding the spanning trees that can be generated, would different if we take all possible adjacency list representations, will that cover all the
We'll
spanning
get
trees?
all the spanning trees. Yeah,
Yes.
no, it will not.
No. But can we prove this, sir? Like, I was thinking about it, but I don't know how to. I was not getting the argument how to show that there exists.
You can prove it. Yeah, you can prove it's not a proof. You can come up with a counter example and then try to prove it.
Yeah, maybe I can. We should think. Okay, I'll try, sir. Then I'll if I can't do, I'll get back to you.
Sure. Okay, so somebody was asking this to repeat this one. So after E, okay, so think of it at E and F, they are at level 2. Okay, now I've taken the first element of level 2, which is E, noted down all its neighbors. They are at level 3, right? All the unvisited neighbors of E. Okay, so you are all at neighbor 3, and now I am done with E, but I am not done with level 2. So level 2, I have to go to the next level, which is not next vertex in the level, which is F. Okay, I am now at F, and in F, what are these neighbors? The neighbors are E and D, but both of them are visited already, right? And this both of them are visited, so there's nothing else that I have to do here. So I'm done with level 2 at this point. Okay, now I go to level 3. So level 3, which all vertices are there? C, B, and D. So I'll go to C first, and then okay, C has 2 neighbors, B and G. Okay, B and G are the level at level. Both of them are already there, so they are already visited, right? So there's nothing else to do. Good. So that is in. We are done with C, but level 3 is not yet done. So go to the next vertex, which is B in level 3. And okay, does B has any? What are the neighbors of B? B has only one neighbor, which is A. Okay, so A is not visited, so I put A. So A goes into level 4, right? See, this is like a distance. So B, the minimum distance from H to B is 3, and A you have to take therefore 4 steps, right? So at this time I'm done with B, but I'm not done with the level 3. So level 3 still has another vertex, which is D. Go to D and say, okay, what are the 2 neighbors? So A and B. So now I say, oh, okay, good. So again, both of them are visited. So nothing to do with D, no, nothing to add with D, but I'm done with level 3 now. So now we go to level 4. And level 4, I find, oh, okay, it's only A, and that's it. Okay. Is this clear?
Yes.
Hello.
Yes, sir.
Okay. Anybody want me to repeat this thing again?
Yes, sir. If you kindly repeat.
Sure. Which part are you finding is tough? Can you just say?
Sir, just the last thing that you have said, I could just disconnect it there.
Oh, okay. Last thing meaning, how last should I go?
Just before means hello. Means
Yeah.
after this B and all, I have heard that after that.
Oh, after B. So after
yes.
B, so say at this point, so we are at this, so say when we are at F, right? So at this point, as you can see here in this top thing, there is something that which has a pointing towards F, which means that I am currently at F. I'm currently understanding F. So F is at level 2, by the way. Okay. F is at level 2. I look at both these neighbors, and both of them are already visited. So since both of them are already visited, so there's nothing else to be done. So I go to the next level. And the next level is C, B, and D. So I take C. I do both of the vertices of the neighbors of C, and both of them are already visited. Again, nothing to be done. So go to, now we are done with C, but not done with the level 3. So next one is the vertex B. So vertex B, we said, okay, what happens to vertex B? So vertex B has a neighbor, and that's the A, an unvisited neighbor. So I put A. So A becomes at level 4, okay, and not at level 3, right? So A is at level 4, and I'm done with B, but I'm not yet done with the level 3. Level 3 still has one more vertex, which is D. And at D, I see that there are two vertices, two neighbors, which is A and B. And both of them are visited. So nothing to be done. So at this point, I am done with level 3, but I am left with A, which is the level 4, right? I go to level 4, look at the vertex of A, and find that there's nothing else to be, there's no neighbors. So I'm done. And there's nothing in level 4. So I'm done with the level, learn the vertex, and that's it. There's nothing else to do.
Okay.
Right?
So in this
Yeah.
particular structure, we have chosen H as the starting node.
Yes. Yes.
So this is a directed graph. If there would have been an H from A to H, so we could have chosen A as the node, and then it would also work, I think.
You could start from anything. Okay. So for example, if you have started from, say, A, what would have been? Can somebody say what happens if I have started from A? What would have been the tree?
Sir, then there will be no H.
No H? What will be there? If I start from A, then what will happen?
So nothing, so you cannot traverse the graph.
A doesn't have any out neighbor.
Yes.
So the game stops there.
Yes, sir.
Okay. If I start from A, then there's no other place to reach. And done. Okay. For example, if I start from C, then I can go to B. Right? So C, if I start from C, okay, I don't have it written up, so you have to do it ourselves. Okay. So let's see what happens if I start from C. If I start from C, C is at level 0. So level 1 will be which one? Can you guys all do it in your
B and G?
So yes, sir, B and G. It will be
B and G, right?
B and G.
Yes.
Right.
Okay. So what happened to the next step after that?
So level 2 will be A,
F and E. A also E. A, F, E.
There'll be A,
F,
and A will be below B, right? F and G, right? Will be under G. Okay. What
So
happens after
starting
that?
from any other vertex, we can never reach H.
We'll not be able to reach H. Will not be able to reach. H will not be there.
Then, sir, what is the purpose of this breadth first search?
Right.
So this, the purpose is that can you reach, if I ask you, right, can you reach H from C? How will you do that? And this is exactly how do you do, right?
Sir, reaching hello.
Yeah.
Sir, reaching H from C can never take this because H has no inward.
Yes, you cannot, but you can see it. You can see it because you are seeing it, right? A computer doesn't know it.
Okay, sir.
So if I give you a graph and I tell you, okay, is vertex U reachable from vertex V? How will you do it?
Then we'll run BFS from C, and then after we have finished, we would have colored them green. If H is colored green, then we can reach. If not, then we can't.
Exactly. Okay? But this thing, if BFS is no special, you can do DFS also. That's also the same.
Yes, sir. If we do the same.
Okay. So whenever you start from a vertex in a directed graph or an undirected graph, your DFS or BFS tree, both of them will only include those set of vertices which are reachable from that vertex. Okay.
Sir?
Yeah.
Sir, if we consider some level 1 node and we look at the this tree that originates from this point as a root, so this is also a BFS, right? with having eliminated all the vertices on which are the sibling vertices and the root vertex. If you were to
Yes, if you
eliminate,
remove all the sibling vertices and all, then yes, that's true.
so the rest of the tree, for the rest of the tree, this is the BFS starting from this child node, from this level 1 node, right?
We have to be a bit careful here. No, not exactly. Okay. So I mean,
So, but
what
then
you are asking is a bit more tricky question. Okay, so you're saying that you run a BFS tree, right? So you have
right,
a BFS tree from H, right?
right,
But now I say, okay, see, G is a
Level 1.
level 1. Now, question that if I have started from level 1, would I get the same BFS tree, right?
In this particular case, we would, sir.
In this particular case, we would, but that is not the case always. For example, look at this F. Okay,
right,
so think that I start from G, right?
right,
If I start from G, I have got E and F are my level 1 nodes, right?
right, right,
And I do this whole thing, right? If you can forget this H to G, the rest of them will be the DFS tree,
right,
right? But F is a level 1 node.
Got it.
If you
No,
start
sir,
from
F is
F,
level 2.
no, I mean, I'm saying the start from G.
Okay, then F is level.
Okay, so then F is level 1. But now if you do a BFS on G from F, then you would have get a completely different set of red colored edges.
Right.
Because you
Sir,
would
is the
immediately
question, sir, is the question whether the spanning tree will be the same or will we get the same vertices? Will we be able to complete it? That is.
Oh, if you are talking about the small vertices, yeah, I mean there will be same. I mean same meaning. Okay, we have to be very careful. This question is somewhat ill-framed, I must say. Okay. Certainly the spanning tree will not be the same. Okay. Now the same thing, right? I mean, if you start from F, now what is it? What do you mean by this set of nodes, right? A set of reachable nodes. Question is that. Let's see. Yeah, so imagine that there is no edge from F to E. Imagine there is no edge from F to E. And you start the BFS from G. Okay. Then E and F are at level 1. Okay. But if you start from level F, then you will not be able to reach E ever. Or you can reach by C. But you can come up with an example, but this will not happen. Yeah, I think you remove this edge from F to E and remove this edge from C to G. So maybe if I can draw this edge.
So, but E is level 1, right? So it is already been.
Okay, let me.
So what is the question from Aniket?
Yeah, so the question is that if you run the BFS from a particular node, right, and then you look at the level 1 vertices, okay, and you take a BFS from the level 1, any of those level 1 nodes, will I get the same BFS tree or not?
So for that we need to remove all the parent, so the level 0 node, all the level 1 sibling nodes, and the tree which originated from the level 1. So
yes, if you remove the tree,
siblings.
then yes. If you remove the tree from what starts from the all sibling, then yes.
Right.
Yeah.
Yes.
Actually, sir, what I was wanting to talk about was
Sir, no, right? Sir, we will not get. Sir, we will not get the same tree. Surely.
No, will not. Unless what he's saying that he is removing the whole. He's considering a completely different tree where he is removing all the vertices that is reachable from
the level
sibling,
1.
from the sibling, all its sibling. Yeah.
So we know that BFS is actually answering the question, what is the shortest path from the root to any other node, right?
Right.
By looking at the level of that node, we get to know what is that path, what is the path length.
Right.
So from level 0 to level 3, we know that these.
No, so okay, so good. So maybe this is something I can say it. Okay, that by BFS you will know the shortest path length from the root vertex to any of the other vertices.
Right. Right.
But from that thing you cannot calculate the shortest path length between two other vertices.
So
that is not possible. Even if one of them is a level 1.
Yes, sir. That makes sense completely.
So maybe because is this because we can have something like
because so I will tell. Yeah, so let me just show you. Okay.
Okay. So
yeah.
we're considering a case where suppose we have a level 1 child node,
right,
and we are looking at the tree that originates from just this child, and we're looking at a
right,
and we're looking at a level 4 node in this subtree,
right,
and we want to show that there exists a path of length lesser than 3 that
or maybe it's
connects
more than 3. I don't even know.
So, but we know that a path equal to 3 exists, which is through this.
No, equal to 3 exists from the root node.
No, sir. What I meant was, if we look at a BFS we constructed based on some level 0 root node that we took.
Oh, I understand. Okay, let me reframe it. What you mean? Okay, I think I understand what you mean. So, say here is a graph, right? And you have started from this vertex, and then you have gone. So this is the, I'm drawing the BFS tree. Okay. I'm drawing the BFS tree here. Okay. And here is, so this is what I started from. Okay. Say X, say I started from. Now I know that at this point, these are all at level 1, these are at level 2, these are at level 3, and so on and so forth. Now take two vertices. Okay. Say I take this vertex, and one in its child. Okay, or maybe this is not a very good.
One as its own descendants. Right. So only consider one vertex and its own descendant.
And its own descendant. Okay. Right. Yes. Then this path is the shortest path between these two vertices in the graph. Okay. Fine. So maybe if I write it formally, okay. So in a BFS tree, okay, so say it's the BFS tree, and I have vertex U and a V, okay, of level of U and level of V are whatever something is there. Okay, I have two different levels, and this BFS tree can start from say H. I don't know what some other number. Now, if you can say that if V is a descendant of U, then the minimum distance from U to V is actually nothing but level of V minus level of V.
Right.
Yes, this is true. Okay, so this is what we are saying, right?
Yeah, this is what I meant to ask. And this is a bit tricky to prove, right? Because
not very tricky to prove. Why don't you try to prove it? It's a very simple graph theory proof, actually. Okay.
Seems trivial, I think.
It's not trivial, but yeah, you have to prove it. Yeah.
So you characterize BFS trees as having only 3 edges or back edges.
Yeah, I don't have to do the thing that is not true, right? So what happens? That means, I mean, there is a shorter path, right?
Right.
And if there's a shorter path, then go and prove it that it should have come at a much higher path, higher level of B should be higher.
Right.
Or lower, whatever. Okay.
So this is a simple induction proof, isn't it?
You can prove it by induction also. You can prove it by induction also.
Yeah, or a proof by contradiction also.
Or a proof by contradiction. Yeah. Okay.
So just asking, I know this hasn't been discussed yet, but why is this not a standard shortest path algorithm?
This is the shortest path. This
I'm
is
sorry?
indeed this is the shortest path algorithm. Don't all it is not.
Oh,
This is the shortest path algorithm.
oh, we just find we just perform BFS and then
You get the shortest path.
oh, okay.
See the shortest path algorithm. But I know what you are asking, and I will come to that later on. Okay.
Sir, is he
Yes.
asking that probably we will not be able to find the shortest path in the best way possible? I mean,
No, you will find the shortest path the best way possible also. Okay, but when we say our shortest path algorithms, what we mean usually is on what is called weighted graphs. When the edges have different weights.
I see.
Right. So we have to minimize the sum of the weights.
Yes, there it will not work. Here, this is what we are doing on weights of all same.
So for the all weight same case, is this faster than that one?
Actually, yes, I think. Yeah.
Oh wow.
So this is indeed the shortest path. If you run it, if you run BFS from any vertex, then. So by the way, one thing that I have not been able to explain you is what was going on top. Okay, how many of you were keeping an eye on this thing?
Sir, I was.
Yeah. So basically, if you remember in the DFS, right? So if you in the DFS thing, this is the depth first search thing. What we were doing was this kind of thing on the side, right? Which was this stack that whatever goes in first will also come out. So that will help us to kind of retrace our path back. Right?
First in, first out.
First in, first out. Right? Sorry,
right.
first in, last out.
Right, first in, last out.
This is first in, last out, okay? But in the stack, in BFS, what we have to do? We have to keep a record of the ordering, right? And this is done by what is called a queue. In whatever goes in first will come out. So it's kind of a double-ended. It's exactly like a queue. I mean, you stand in a queue in a line, right? Whoever stands first will go out first. Right? Everybody stands in a queue, and and you go out as you have entered. So here, for example, you start with H. H has entered the queue. Okay. So at this point, I'm at H. Then I said, okay, H has one vertex, which is G. Okay, I put this G and I go to, and H is done, so I go to G. Now, see it here. Now, here is the beautiful part. Okay, so G has two vertices, E and F. So I write down E and F, and I'll be done with the G, right? I will write down E and F, and I move to the next vertex. Then I said, okay, E has three more things, right? E has C. I go and visit all of them one by one. E has B and E has D. But when I say E has D, I'm done with E and I move to what? F. And this is exactly where I'm supposed to move, right? Because I've done with E. So what is happening is that all the vertices in the same level are coming together in the correct order. Okay, so see here, this H is level 1, then G is level, so H is level 0, G is level 1, E and F are level 2, C, B, D is level 3. Okay, if F had another vertex in another neighbor, which is a new neighbor, that would have come after D, and I would have got 4 level 3 vertices, one after another. Okay. So, I mean, this arrow, you can think of it as kind of moving arrow. So, I mean, you should not look at anything beyond this. So at this point, I am F. So, F is the first in the queue. In some sense, I'm thinking of that this G, A, G, and E have kind of left the queue. Okay. So, the arrow kind of says that who is first, and the arrow will only move right. Okay. So, at this point, I am at F. I look at F, I look at the two neighbors, E and D. Of course, they are already visited. And so I move to the next one. And see, I'm done with level 1. So I should go to the, done with level 2. Now I should go to level 3, the first vertex, which is magically has been already there. Right? Then I go over C, then I see B. At this point, B has a neighbor which is A, and I have put it there, and I get level 3 over here, and level 4. So prove that, okay? So this is how I want you to prove. Okay, think, yeah, go ahead.
So for writing an algorithm, we can mark it like once all the neighbors of a particular vertex are marked, we can just remove that vertex and go start the we are using the queue, so we are removing that first vertex. So
yes. So as soon as, so like we did for the DFS, if you remember, right? What will we do? As soon as I am visiting, so as soon as from E I visit B, I will remove B from the neighbor of E. Done. Okay. As soon as I see D, I remove D from the neighbor of E.
So what do you mean remove D from the neighbor of E?
From the adjacency list.
So, this algorithm does not leave the graph untouched, so to speak.
Okay, it doesn't grab the, okay, we can either remove the D physically, or you can again mark it out accordingly. Right.
So why do we need to do this? At each step, we can just check if after encountering something, whether it is in the queue already.
No, that is fine. That I can do. Oh, but that is harder. Then how much time will it take? How many times will it take if I have searched for every vertex with a
login at least?
More than login, not sorted.
Right, n.
So that's another additional.
Right.
So this removing is or marking it, whatever. Okay, doesn't matter what you are doing, but that would help us to kind of not revisit the same thing again and again.
Right.
Sir, and we're calling this data structure a queue because of the moving arrow, right? That arrow is representing
yes.
the head of the queue.
Yes, the arrow is the head of the queue.
Okay.
Whoever comes will add in the back, and the arrow will always keep on moving, right?
Right. So this data structure has a twofold purpose, right? This is one of them is memory storage, and the other is traversal of the graph where edges are not available to traverse through some of the vertices. So if we are looking at two siblings that are not connected, we still need a way to get from one sibling to the other.
Yes.
So this queue will help in that sense. And
So
even in the
why
DFS,
do we need to get from one sibling if they're not connected?
No, so we don't have to, not for BFS, but he's saying, I think from somehow if you want to kind of think about how to go from one to the other.
So I meant from, in this example, like we went from looking at the
oh yeah, we don't want to, yeah, right. I mean, after we are done with B, I want to go to D, right? That's what you mean.
Right.
Yes, after I'm done with B, I am going to T. I'm not going along an edge. I'm going just along the There's no reason to have a edge from B to D. Just because D is next in the queue, I just jump to D.
Right, and even in the DFS, we needed a way. So if we had a directed graph, we would not have any edge traversal way of backtracking. So we would need that external.
Right, there's no edge here. Now, unlike DFS, when every movement happens, we kind of go from one vertex to according to this graph that is being formed. Here it is not. Yeah, that's a very good point. That's a very good point. Yes. In the DFS, when we move from a vertex, I mean, when I am looking at a vertex A, then I go to vertex B, it has to be that A has to be connected to B in some way, right? Either there's an A path from A to B or the B from B to A. But here there's no such reason. There's nothing. We can jump from B to B.
So actually in DFS, we might have a directed graph. So when we're backtracking, there may not be an edge.
Yeah, there might not be a, I mean, no, there is an edge. There's the edge in the other direction. but some edge is there.
Oh, okay. So I thought that the direction matters if you want to traverse.
That doesn't matter, but I'm just saying that this is an observation. This is nothing that is not change the algorithm as such.
Okay. Right.
I mean, it's not a, I mean, like here also, when we are doing from, say, I am right now looking at, say, D, and when I pop out D, I'm going to F. I don't need to walk along this edge. All I say is go to F and start. Right. So there's no reason to go along an edge. But I'm just saying that you have made a nice observation that there is a connection between D and F. Okay, but in the case of BFS, there need not be any connection.
Right.
Right now I'm looking at B. The next thing I will look at is D, but D might not have any connection to B.
Right.
Either forward or backward. I'm just saying it doesn't matter here in the algorithm anyway, but it's a nice observation that you have done.
Okay.
Okay.
So, can you repeat the observation?
So observation is that, say in the case of BFS, what is happening? Okay, so I have this stack in this side, right? At this point, I'm looking at F. Okay, so see, as I look at this stack, okay, I will first look at F, then I will look at E, then I will look at B, right? Something like that.
Yes.
But that means that there is either there is an edge from F to E or an edge from E to F. Has to be there. Similarly, there is an edge from B to E or from E to B. Has to be there.
Yes.
Okay. I mean, that's a kind of a, I mean, you can guarantee that if you look at the whole stack, at any point of time, this stack is a kind of a, it is not disconnected in some sense. Okay, there is an either from A you have to go to B, from B you have to go to E, maybe there is a backward edge also, or something like that, right? But in this case, that is not the case.
Okay, yes. True.
Between any two vertex in the queue, they might not have any connection. Okay, so how do you prove the correctness of this queue thing? I will just ask you guys to kind of prove two things that you can prove for yourself. Okay, number one is that if I'm actually one thing is good enough. Okay, if U is visited before V, then U is before V in the queue. I mean, it's an obvious statement almost. I'm like, it's an observation. Okay? And that's all that you need. Just with this observation, you can prove that the correctness of the BFS algorithm.
Sir, if U is visited before V, then that's how the queue would be made, right?
That's how the queue is made, right? So, okay, there's another observation that you have to see, okay, which is if U is at level I and V is at level J and I is less than J, then U is visited before V. So this is a, yeah.
Sir, what do you mean by the correctness of BFS?
Yes, sir, same question.
The correctness of BFS meaning, see, yeah, I have told you the algorithm. Okay, so I have not even told you the algorithm actually. So let me just give you the algorithm. So here is the algorithm. First of all, I have to do this queue. Queue has two operations, okay? It has this two operations, which is NQ, meaning you put the element at the end of the queue, and there's a DQ, which basically removes the first element. Okay, so it's just like stack, but in stack it removes the last element, the element that was entered last, and here the element that was entered first is removed. And here is this algorithm. Okay, you start with an empty queue. Okay, initially all of the vertices are colored gray. I start with putting this starting vertex in the queue, in the NQ. And then as long as the queue is not empty, this is what I do. I first consider the first vertex in the queue, so I let it be U. Okay. And I look at all the neighbors of U. If the neighbor of that W is gray, that means that has not been visited earlier, I just put them in the queue. Okay, and I color it as, and I remove it from the label. And that's it.
What is select UW does?
So select UW. Select UW is basically in this algorithm. If you see that this is basically this age is basically selected as the age of the BFS.
Okay.
Okay, the coloring of the age here. Yes. Okay, so the select UW is basically selecting that age UW as the age of the BFS tree. Yeah.
Aniket, go ahead.
Oh, okay, sorry. So if we get the color of W is blue in this clause, then don't we want to?
Oh, then also we have to remove it. Yes, that's.
But then what was the purpose of removing this edge if it was blue?
If it is blue, then I again still don't want to kind of revisit it again, right?
So, but then where in this algorithm would we have to revisit it again, even if we don't remove it?
Actually, you are correct.
Sir, if you're coloring it, then there is no need to remove it, because then we can include.
You're right. You don't need to remove it. That's
yes.
Because it's a progressive algorithm,
right.
So we wouldn't ever come back.
That's true. Completely. You don't need to.
Right.
Yeah. So what was the other question?
So I was asking that if you could explain this algorithm, I mean every line with what you said in the algorithm.
Yes. So okay. So these are the first three things: the initialization. Okay. So I have an empty queue, right? And I start with coloring every vertices of the graph as gray. Okay. And I want to start from V, right? So here's the BFS of GV, meaning I want to do the BFS starting from the vertex V. So I start with putting the vertex V in the queue. Okay. And then what do I do? Let's go back here and see. Okay. What is it that we are doing? Just look at this one. Okay. Keep a tag on this one. Okay. On this top one. This is what we are after initialization. H has been put in the queue. So next thing, what you do? You look at the first one and say, okay, you are the first one. What do? You give me all your neighbors, and if the neighbors are not visited, if the neighbors are not visited already, then put them here. What does neighbors are not visited meaning? Neighbors are not visited meaning the neighbors are not neighbors are gray, right? Neighbors are not blue. Okay, if the neighbors are gray. So I do few things here at this point. I take H. What is H? H is now the first element of the queue, right? Take the first element of the queue. Look at all its neighbors. Whichever neighbors are not visited yet, put it back. Put it here in the queue. Okay, put them in the queue. And what's the other thing? I want to color this H and G. H to G as red, right? Or I want to basically select this particular H and done. Okay, that is done with H. The next thing, what do? I go to this next element, which is currently the first element in the queue, right? The pointer is always pointing to the first element of the queue. I am basically saying that, okay, again, DQ yourself, meaning G is the DQ, the first element of the queue. And I do the same thing. I look at all its neighbors, and one by one, I will see if they are gray, I will put it here in the queue. So So at this point, E is gray. So I take E, put it in the queue, and color this edge GE red. Now I look at the next one, okay, which is the next vertex. Next neighbor of G is F. Okay, give me this neighbor of F. F is gray, so I put F back in the queue and color it red, and I go to the next element in the queue, which is E. Right? Again, I do the same thing. Again, E, I say, okay, give me all your neighbors. So what are your neighbors? Okay, C is your neighbor. Very good. Put it back. It is still gray, therefore I put it back. Put in the queue, and similarly do for B. So next neighbor is B, which is gray. So I put B in the queue and color the edge EB as red. And any other thing, D. D is also gray, and I put it in the queue and color it red. So at any point of time, I'm looking at the first element in the queue, and I'm doing this. I'm going over all its neighbors. If they are gray, I am putting it in the queue and coloring the edge. Right? So at this point, I'm at F. So F has two neighbors. First neighbor is E, but E is not gray. E is already visited. So E is blue. Okay, so I don't do anything. F has again another neighbor, which is D. Okay, D is already blue, so I don't do anything. And that's it. Right? So I keep on doing like this. So this is what we are doing step by step, right? And that is exactly what is written here. See. So while, and okay, by the way, when do I stop here? I stop when I have hit the last element in the queue. There's nothing else to continue. Right? So this is what. So while the queue is not empty, okay, you take the first element. That is the vertex that we are dealing with. And do this one. Look at all the neighbors for all W, which are neighbors of you. One by one, you do this. You check if the color is gray, and if it's not visited, then you do these two operations that I told you. You NQ, meaning you put it in the queue, and you select the edge UW. Okay. Also, you have already visited, right? You have moved, you have already visited now W, so I have to color that W blue. And I'm also doing this one that I have already visited W, right? So I kind of can remove W from its neighbor of it. But as your friends pointed out, this line might not be default as such. So that's it. So this is the while loop. The while loop is for all as long as the queue is not empty. And then this is like for all neighbors, take an element of the queue and do this following. Is it clear?
Yes, sir. So, sir, I mean, at no point of time, this queue is contains all the vertices at a single time, right?
No.
That's where the confusion is. Okay.
No, yes. The queue will not contain all the vertices. Because as soon as I'm dequeuing it, I'm throwing it away.
Yes, sir.
Okay. Good.
Sir.
Yeah.
Sir, I don't know. Sir, in the third line, when we are enqueuing, when we're initializing the queue, after that, shouldn't we change the color of V to blue?
Oh, you are right. Very much true. You should do that.
Otherwise,
you should do that. Yeah, good. Very good point. Yeah, nice observation. Yeah, you should do that. At this point, we should change the color of V to blue. Yes, completely right. Very good. Very good point. Yeah, I should kind of edit this. Every year I kind of teach the same thing and then I forget to edit this slide.
So
okay,
if you don't make that edit, where is the problem?
So if you don't make that, then it might be that some other vertex later on will find there is an edge from say U to V. So at this point, there is an edge from U to V. So I say, oh, V is still gray. So I'll put V back in the queue.
Right.
Right. And that's like a bit weird thing. So V is of course level 0, and now I'm putting it at the place of level I, which is wrong.
Right.
Right?
Yes.
Right. Oh. Good. Any other questions, doubts? Okay, good. So if this is if you have understood this one, okay. So I think the rest of whatever is there today is very simple. I mean, okay. Yeah. So this is something that was there. So basically, you can check connectivity with it. So if at the end of the day you start from V and you ended up coloring U, the color of U to be also blue, then you know that, oh, that means there is an H from the path from V to U. This is this is something nothing special about BFS as such. There are DFS also has the same thing, right? You can check the connectivity. This is something. So if you remember in the last class, we were doing with this graph. So let me just draw you another example, another graph. Okay. Think of maybe under. Okay, so now say that say this is, so this has been, so this all of them have been chosen, okay, and this edge has not been chosen. So this is the graph and the red ones have been there. Is this one a possibility? Oh, so no, I have made a mistake.
So one of the level 3 nodes has a depth of 2 or a length of 2 from the root node, so it's not possible.
So what's the problem here that can happen? That when I was dealing with this particular vertex, right, I should have put it, I should have visited this vertex right away as a neighbor, right? So I should have just put this vertex up here, correct? Right.
Yes, sir. Yes, sir. So, so if we divide all the vertices into level sets, then two level set edges should be connected, not
exactly. There cannot be a tree graph edge, even a graph edge, forget the tree edge, a graph edge between level I and anything more than I plus 1.
Yes, sir.
Okay.
Sir, there cannot be what?
So if level of U is the I and level of V is bigger than or equal to I plus 2, then U comma V is not an edge in the graph. Okay, because when you were dealing with, so you must have been dealing with U at some point of time. At that time, V must have, V is the neighbor of U. So if this is not the case, if U V is the edge, then when you are dealing with U, you would have looked at V and you have put V right at level I plus 1, not I plus 2. Right here. So such an edge is not possible. Is this clear? Or should I repeat it?
Yes,
Sir.
Yeah.
I mean, the graph can contain the edge, but the BFS tree won't contain the red edge.
No, this graph itself cannot contain this edge. If graph contains this edge, then the BFS tree cannot be this.
Oh, I mean, given the BFS already.
Given the BFS tree is the red edges, right?
Yes, then the edge cannot be contained.
Yes. Okay, so if this is the graph actually, then the BFS would be not like this. Then how will the BFS be? The BFS tree will not be here, it would be here. That would be the BFS tree, right?
And there would be a black edge.
And then there will be a black edge from here to here. There will be a black edge from here.
Yes, sir.
So this will be the tree, not the other one, right? So similarly, there cannot be an edge. There cannot be an edge like this. Forward edges are not possible. Not possible. Same reason, right? So this is what is there. So you can have the free and non-free edges, and only a particular kind of non-free edges are allowed. So as we kind of saw there, the forward edges are not possible. So you can have free edges. You can have backward edges. Backward edges are very much possible. Okay, that is no problem. What is backward edges? There can be an edge like this. That is perfectly fine. Okay, this is okay. So there can be free edges, then backward edges, and then there are cross edges. But these cross edges also are with something that we have to be careful about. Cross edges between nodes of level difference less than or equal to 1. Okay, so no forward edges or switches can be there.
Sir, but there are further restrictions as well, right?
There are
On
further restrictions
edges.
also. Yes, you can put some more restrictions.
Like for instance, we could have. So could you just scroll up? Sir, and can you just
Yeah, so
label
there
the
cannot
leaf
be.
nodes?
I know what you are saying. I know what you are saying. I will tell you. There cannot be an edge like this. Can this be an edge? That is also not allowed.
So this is also fine, but
No,
then
it's not. It's not.
If we
Then the first level that should be the node.
Huh?
The first level there that should
Yes.
also.
When I am
be the
dealing with
same.
this vertex, then I should have put in this. I should have, when I am dealing with this vertex, I would have put this vertex as this child, not as this child.
so but what if we started from the right?
Yes, so I'm again assuming that I'm doing everything from the left. So this ordering is from here.
Okay. So, but we can also say that, okay, let's make the symmetric node, which is just reflected. If you can just join this node that you just highlighted to right.
Yes.
So both of these edges can't exist. Only one of them can exist. If there's
only
no
one of them exists, exactly.
Right.
Yeah, but this kind of edges are fine. This is
right.
Yeah. So just, I mean, this is something that you should kind of might want to play with it later on in various problems and all. It will come out when your understanding of how the BFS tree structure become very important.
So is there a name given to that phenomenon where we had that higher
No
connectivity?
particular kind of particular names are there of this kind of. They're all cross edges of different kinds.
Okay.
Yeah. So by the way, the running time of this algorithm, as you can kind of have seen it also possibly. So again, the same thing as within DFS. We are going to go look at every edge from U to V and edge only once or twice if it is undirected. U to V and V to V. So in the same way as in the case of DFS, our algorithm will run in order V plus E steps. So it's a linear algorithm. Right?
So here too, every edge is being considered. So here too, every directed edge is being considered once, right? Like in the DFS.
Yes. Yes. Every directed edge is considered exactly once.
But this is slightly lesser complicated because of the coloring. involved. There
Yeah,
was
slightly less complicated because you don't have to. Yeah, but I mean they're kind of same. If you think of it, both of them are not too complicated in any case. Yeah, so in DFS there were 3 kind of coloring. You are right. To some level. In DFS there are 3 kind of colorings. First it is gray, then it was blue, and then you're done. That has to be put up there also.
right.
Also, BFS do some things of in very handy, like up path, the shortest path.
Yes.
When all the edges have one same weight, identical weight.
Exactly. So that's a very good point. So this application of BFS is one of them is that there is a shortest path between from a vertex to another vertex can be done using BFS. Very easily. But BFS also has its advantages, right? Like topological sort is exactly a reason why people do BFS.
Topological sort can all be done with the DFS, right?
Can be done only with BFS. BFS will not give you. You can try it out.
Oh,
No,
okay,
BFS
okay.
we can't do it. No.
Okay, so to think of it topological sort. Topological sort is BFS will not give you topological sort. Okay, so topological sort only will happen with BFS, and that I left you for you guys to think out which one, the finishing time or the starting time of BFS. Yeah, so I mean, there's
So
nothing
that's
particular.
because
Yeah,
BFS is allowing back edges, right? In the DFS, there were no back edges, or for at least a setup where a
I
topological
don't know
sort
whether
is
because of
possible.
that. Yeah, maybe you are right. Maybe it's, I mean, on the high level that is what is happening. But
Okay.
yeah, at the high level that is what is happening. But
it's more even more fundamental why it won't give us a topological sort.
yes.
Okay.
Yeah, so I think I have done this one. So basically, there's these levels that I have kind of discussed here, right? I mean, you can get the distance from anything. So these are what is called a single source. Means from H, you get the shortest path not to one vertex but to every vertex, right? So that is also a very useful thing to have. And yeah, so of course, as in just like in DFS and BFS, both of them you can check connectivity. You can find out the components, connected components. You can check whether there is a path from U to V, and particularly for BFS, you can also get the shortest distance from U. And that's it. So that is all that is there in for BFS. Okay. So if you have any questions, I'll be happy to take questions on BFS or DFS or anything. Okay. But we have just discussed two of the most fundamental graph traversal algorithms. One is DFS, one is BFS. Okay. They have huge applications, unbelievable applications. And the applications many of times are related to the structure of the BFS tree or DFS tree that comes in. I mean,
Sir,
of course, this, yeah. Go ahead.
Sir, I have a question.
Yeah.
Is there any does there exist any algorithm that do a graph traversal in less than big of mod b plus mod t?
No, they cannot. They cannot.
Okay.
Okay. Why cannot? Because the input size of the adjacency list itself is order v plus e, right? So if you do a graph traversal, you kind of say that you kind of are not going to read the whole input. Okay. And this is something that you can almost take it to prove it also, that if you don't read the whole input, okay, then I'm not saying that always it will give you a wrong answer, but then there will be some cases where it will give a wrong answer. Okay.
Okay,
so,
sir.
So you have to read the whole input. Okay. So for example, you have possibly not read one particular vertex or something. You don't even know that there is another completely new edge that might suddenly vertex might have suddenly appeared up in its neighbor. So these are called linear time algorithms because the input size is same as the output, the running time of this algorithm, BFS and DFS. Okay. And we will be using this algorithms a lot, at least as a kind of a very basic thing to check the connectivity, to check the shortest path, and so on and so forth. We will use them a lot. So, so again, I think I have told Omkar, I know Omkar will do it also. We'll upload a set of questions on DFS and BFS before tonight. Please try to read them, answer them, solve them, whatever. Okay, and come tomorrow and discuss. Okay, for example, I've kind of, if you, I'm sure some of you will be thinking of the topological sort. Okay, what is the topological sort? Meaning, as I told you in the last class, DFS, there are two different ways of, like, for example, here also there are two different ordering, right? Actually, there the ordering, it doesn't matter that much. There is only one ordering, which is the first time it is visited, right? But then there is an ordering which is in the DFS, so in the first time it is visited and when it's the last time it is visited. Now, which ordering will give you the topological sort and why? Okay. Think about it. It's pretty simple, but you have to think about it. Yeah. So, any questions other than whatever was asked already? Hello.
Yes, sir. We can hear you.
Okay. So, if you don't have any questions, that's perfectly fine. So, please try to read this DFS and BFS. Solve some questions. We'll be uploading it in the next class, which is on Tuesday. We will go into a little bit more involved graph algorithm. So we have given you graphs. We have told you how to check whether it's connected or not, how to find the shortest path, how to output a minimum spanning, a spanning tree. But now, the next class will consider graphs which are slightly more structured, namely weighted graphs. So graphs where there will be weights on edges. Every edge has a weight. It's very much similar to a kind of a road network. Okay, there are cities and then there are roads from between two cities, and the road and the edge represents the distance between two cities. Okay, they can have a special number. And the question is that we want to ask, in this kind of weighted graphs, what is the shortest path between you two? In this kind of graphs, can you come up with a spanning tree which is minimum cost, or which some of the edges in the spanning tree is minimum? Okay, so these are the two questions that we will be trying to answer next. Okay, so basically, from the next class, and this is what will be there in your before your mid-sem also. We will be looking at weighted graphs. So weighted graphs are graphs where you have the vertices, the edges, and a weight which is from the edges to real. Sometimes it can be positive or sometimes it can be negative. And we are interested in the distance from U to V, okay, which is the, so sum of the weights of edges EI such that the path, say, path, no, sorry, such that let me see. So what is the minimum distance? Okay, let me formally write it. This is, yeah. So minimum over what I am telling you. Okay, minimum over the weight of U to V1 plus summation of weight of vi plus 1, okay, where I equals to 1 to say k, plus vk plus 1 comma v, and the weight over all such v1 to vk. So basically it is the path. Consider the path, consider any path that goes from u to v, and consider the weight of those paths. Okay, the path that minimizes the distance, meaning the weight of a path is the sum of the edges, weight of the edges in the path, and the path that minimizes the distance is this, of course, where all of them have to be edges in the graph. So how do I find it? Okay, so find uv in the distance of it. This is the next thing that we will ask. Another thing is that what we will be asking is finding minimum spanning tree. We have given you this BFS and DFS that will produce you a spanning tree, but a spanning tree always has n minus 1 edges, right? So minimum spanning tree what? So weight of a spanning tree is the sum of edges, sum of weights of edges in the. This is what is also called a MST. So these are the two questions that we will try to answer. Okay. So now that we have understood how to deal with graphs a little bit, how to go with DFS and BFS, now we will go into this weighted graphs. And before the mid-step, these are the two things that we will be doing. How do you calculate the minimum distance between two vertices, minimum calculate in a weighted graph, and how do you find the minimum spanning? Okay, I think if I'm not wrong, I think we have only, how many classes are there before our mid-sem? 3 classes, is it? You guys remember?
I think so.
Yeah, next week there is only 1 class. There is a Diwali break.
And the week after, right?
Yeah,
Yes,
so I
sir,
think
3
there's only
classes.
3 classes. Yes, so it will be perfectly fine for this. Okay, so but please try to come and clarify your doubts. Try to solve this BFS and DFS as much as you can. Okay, and clarify your doubt with me or with your TAs. And yeah, so that's it. So okay, so thank you. And I must say that I'm very happy with this class, that many of you participated wholeheartedly. I really wish that you continue like this.
Thank you, sir.
Okay.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Bye.